Hi, today's lecture is on fractals. Now, fractals may not be in the mainstream of statistics, but they're so pretty that I thought I would start off with something which would sort of relax you, bring you into the fold a little slowly, and let you enjoy. In fact, I do want you to enjoy all of statistics. So let's get started with fractals. The key thing in fractals is a term called self-similarity. What's going to happen is that we're going to see that there's self-similarity in the pictures that we draw. Now we're going to start off with what's known as an initiator. An initiator is just some geometric figure. In this case, it's a triangle. It could be a square, it could be a straight line, it could be a five-sided figure, or a six-sided figure. It could be anything that we want to start off with to give us sort of a general outline for our picture. That's called an initiator. Then there's a thing called a generator. A generator is what's going to be used to replace each line in the initiator. That is, the initiator, if it were a straight line like this, would be replaced by a generator, which would look like this, so it would, that line would now be looking like that, be replaced. And we'll see that. Let's just get on and see it. We're going to talk about first something called the von Koch snowflake, a classic fractal, von Koch snowflake. Now the von Koch snowflake starts out with a triangle. That's its initiator. Its generator is the generator I showed you a moment ago, and that means that each line is replaced with something looking like this. And so the next generation of the von Koch snowflake would look like that. And that's what the computer says it looks like. So it looks like just what we thought it would look like. The next generation, we replace each line in the figure with the generator, so that this line is replaced with this. This line is replaced with this. This line is replaced with this. And you can see what's happening if you go on and on. You get a picture that looks like that. See? And now, continuing on, this line is replaced with this. This line is replaced with this. This line is replaced with it, etc., etc., all the way around the figure. So the next generation in the creation of this von Koch snowflakes looks like that. And now you replace each line with, again, the generator, and you get a picture that looks like that. And pretty soon you're going to hit the resolution of the screen. Now we can see a little straight lines here. Let's go one more time. Now, I think now they sort of look kind of smoothed out. If you took a magnifying glass to it, you'd see that there's lots of little squiggles inside what looks like straight lines here. Okay, is this a fractal? Well, first of all, what about this self-similarity thing we talked about? If I look at this here, I see three main bumps protruding and a lot of little jiggles on it. That's the general picture. All right, let's look at a piece of it, this piece. What do I see? I see three main bumps with jiggles on the inside. Oh, well, let's look at this piece. What do I see? I see three main bumps with jiggles on the inside. If I were to magnify this piece, now you can't see it on your screen, it's far too small, but if you would magnify it, it would look again like these other things looked. The smaller ones are similar to the big ones. In fact, in this case, they're identically similar. If you actually expanded it, you would see that they would fit exactly superimposed on the one before it. This is extreme self-similarity. The little pictures are similar to the big pictures, which is part of itself, so it's similar to itself. Self-similarity. Okay, we talked in the notes you saw a discussion of the fractals and the coastlines and the dimension of this coastline. Well, here's how you calculate the dimension for a fractal, for this simple fractal, for the von Koch snowflake type of fractal. If you look at the generator, and the generator we saw for the snowflake looked like this. If the line here it was replacing was 1 unit long, then each piece is 1/3 of a unit long. 1/3 of a unit long. And there are 4 pieces to the generator. And the dimension of a fractal can easily be obtained by taking the logarithm of the number of pieces in the generator divided by 1 over the length of each piece. The length of each piece is 1/3, 1 over it is 3. So for the Von Koch snowflake, the dimension is log 4 over log 3, which is 1.2618. Well now, should you remember 1.2618? No. The important thing to remember is that a fractal, although it's drawn in one dimension, it has all these squiggles down to an infinite dimension. All the way down you see little squiggles, so that the total length of this fractal is really infinite. And yet, it doesn't fill up a whole plane. If it filled up a whole plane, it would be 2 dimensions. Since it doesn't fill up a whole plane, it must be a line, which is 1 dimension. But a line has just a finite length. Here we have an infinite length line. So people say, well, it's somewhere between a line and a solid, a line and a plane. This is 2 dimensions. This is 1 dimension. A fractal is something in between that. It has a dimension somewhere between 1 and 2. Dimension of fractal is somewhere between 1 and 2. When you get 1, you have a line. It's just a geometrical figure. When you have 2, you have a plane area. It's not a line. It's not an area. It's not a line anymore. It's an area. 2 dimensions. 2-dimensional figure. But if it's between those 2 numbers, it's a fractal. So it doesn't matter what this number is. You don't have to memorize the number. What you should realize is that the fractal dimension must be between 1 and 2. And exactly what it is will depend on the particular geometry of the generator. Well, there's another one I'm going to show you, the 3-segment Von Koch curve. It's going to have 3 sides. Each length is going to be the square root of 1 over the square root of 5, or each length will be 1 over the square root of 5 of the whole length. And if you plug log 3, log square root of 5 in here, you get 1.3652 as the dimension. Well, its dimension is between 1 and 2. It is a fractal. We're more interested in what it looks like, so let's do it. Here's the initiator. The initiator in this case is just a square. The generator looks like that. There are 3 pieces, that's why n was 3, and if this is the whole length, if this is the unit length, this length here turns out to be 1 over the square root of 5 of the whole length. 1 square root of 5th of the whole length. That's what this length is. Okay? So with that as the generator, funny looking generator, we replace the square. And oh, how is that? Well, here was the square. And what happened is that this line was replaced with this figure. And this line was replaced with that figure. And this line was replaced with that figure. And this line was replaced with that figure. And so you end up with this cross shape. Now, if each line in this cross shape is replaced with something like that, you'll find that you end up with a picture looking like that. So that's the next generation of the 3-segment Von Koch snowflake. And if you go another generation, it looks like that. Another generation looks like that. We're beginning to find that the little twists and turns are very small, very difficult to ascertain what's going on. That's almost to the beyond the readability of our screen. One more ought to do it, and that's it. It doesn't pay to go any further than this in generating the thing because we can't see it on the screen. We can't see down any further than this. But theoretically, this goes on forever. Smaller and smaller and smaller little boxes, little boxes. Well, look what we have here. Let's just take this piece here. What have I got? I've got 2 big humps. A little hump on before the big humps. And the big humps are made up of other littler humps. Okay, well, let's look at one piece of it, this piece here. What I have here is two big humps. A little hump before the big humps. And the big humps are made up of littler humps. All right, let's just look at one piece, this piece here. Two big humps, little humps before the big humps. Let's just look at a little piece here. Two big humps, little hump before the big humps. And no matter how small I get, I got the exact same picture. Again, the little pictures are similar to the big pictures. Well, this is all one body, one picture, so this is similar to itself, self-similarity. Let's look at the 8-segment von Koch curve, 8-segment. There'll be 8 pieces to it. Each will be a quarter of the total length. And the dimension is going to be 1.5. Again, it's between 1 and 2. That's really all we have to know. Certainly don't try memorizing this stuff. The initiator is a square. The generator, 8 segments. Each segment is a fourth. Notice that if this is the line it's replacing, each of these pieces is 1/4 of the total length. So 1/4, 2, 3, 4, 5, 6, 7, 8. There are 8 pieces, each 1/4 long. That's why the dimension is log 8 over log 4, which is 1.5. Now, if I replace each line in the square with my 8 segments, it looks like that. And now I replace each line in that with my 8 segments, and it looks like that. And now we replace each line with 8 segments, and it looks like that. Now we place each line with 8 segments, and it looks like that. And that's the limit of accuracy in the screen. But of course, these little pictures go on forever. And again, I'm pretty sure you can see that here I have 2 big humps. 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 No matter where you go, you have 2 big humps. And the picture is similar. Each picture that you get, smaller and smaller picture, is similar to a bigger picture, self-similarity, which is a trademark of a fractal. Now I'm going to throw you a curve here, a piano curve. It's going to have 9 segments. Each segment is going to be 1/3 of the total length. So 1 over 1/3 is 3, and log 9 over log 3 turns out to be 2. That means it's not a fractal, it's an area. We have something that has an area. Well, let's look at it. The initiator is going to be a straight line. The generator is going to be, length is 1/3 of the total, so length is 1/3. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. N is 9, R is 1/3. So log 9 over log 3 turns out to be 2. Well, why is that 2? Let's see what happens. So we replace the initiator with the generator, and we get this picture. Now we replace each line with the generator. That is, the first time we replace it, we got that picture. Then we replace each of those lines, and we get this picture. Now we replace each of those lines, and we get this picture. And we replace each of those lines, and we get this picture. And actually, I decided not to take it any further because the next step had the lines so close together that the picture came out blotchy. You can't show a solid thing blotched on the screen. But the squares are getting smaller and smaller, and eventually it just closes in. And we have a solid area. The dimension of this fractal, this would-be fractal is 2, and therefore it's not a fractal. Okay? Here's one that's a classical picture, Sierpinski triangle, a Sierpinski triangle. There are 3 sides, each of length 1/2, and dimension is 1.585. The 3 sides look like this. Each one is a 1/2 unit long. So there it is. That's the generator. And the initiator is going to be just a straight line. We'll start with a straight line, and we'll replace the straight line with this. So that's the first generation. Now I'm going to use a little bit of trickery here. I'm going to switch direction of my angles each time. So I'm replacing this with something. The first this next time that I use it, I'm going to replace it in this direction instead of in the other direction. And now I'm going to switch angles. I'm going to replace it in this direction, the positive direction. Now I'm going to switch again and replace it in the negative direction. But you see, I am replacing lines with this triangle. That's all I'm doing. But to make it look the way I want it to look, I'm switching the angles of my replacement each time. And now the next time, I will be replacing this with something like that, and this with something like that. And when I'm done, the picture will look like that. So that's the next generation of the Sierpinski triangle. And the next generation. And the next generation. And the next generation. Beginning to take on a form. And the next generation, and that's where I'm going to stop, because everyone knew the Sierpinski triangle many, many years ago, before they even thought of fractals, as a very simple thing. You take a solid triangle and you cut out the center of it, the center triangle of it, and throw it away, making it clear. Now you'll have three big triangles. Take the center of those and throw them away, clearing them up. Now you'll have 9 triangles. Take the center of those and throw them away. Now you'll have 27 triangles. Take the center of those and throw that away. Then you'll have, and so on and so forth. Keep throwing away the center of each solid triangle you get. And when you do, you get a very, very holy triangle. It's got no area, but it sure looks like it does. What it is the Sierpinski triangle, a very strange mathematical shape, very interesting to mathematicians. Okay, what does this have to do with statistics? Well, nothing. Nothing. So far, at any rate. Fractals is known to be the geometry of nature. I can't show that here. This is not a course in biology or engineering, but geology. Natural things don't take on mathematical shapes like circles and triangles and rectangles and squares. They take on geometric shapes that resemble fractals. And fractals are then, people are trying to use fractals to imitate nature, to model nature, to show what nature is doing, to understand nature a little bit better. There's a problem, though, having a problem. And the problem is that, sure, you look at a snowflake. To the naked eye, it looks like a perfect geometrical shape. But if you go closer, to take a magnifying glass to it, of course, after you freeze it and take a picture of it, take a magnifying glass, you find that it's not precisely a fractal. It's not exactly what it should be. You take a natural stone that's formed over billions of years, and it looks like a fractal, but if you investigate it real closely, you'll find that it's not exactly the mathematical form it's supposed to be. Something's irregular about it. And what is irregular about it is that nature is not completely mathematical. It has in it a random component. And that's where statistics comes in. Statistics is a study of randomness. We're going to be studying plenty of it. So if you add a random component to the fractal creations of nature, you get things which are more realistic. Okay? So adding a random component makes things more realistic. And we're going to try and make things more realistic. What we're doing is creating a realistic picture of the universe. So although fractals are the geometry of nature, random fractals are the actual geometry of nature. Now, I'm going to show you that you really can't tell the difference. Here is the pure Von Koch snowflake. Pure Von Koch snowflake. Look at it. And now I've added a 5% error to all the angles and all the lengths in this snowflake. 5% error. You took a magnifying glass to this next picture. It would differ from the angles here by approximately, on the average, 5%. Now, they look to the naked eye exactly alike. There's really no way you, looking at them as a big picture, could tell the difference. Let's look at the 4-segment Von Koch snowflake and adding randomness to it. You'd be hard-pressed to show that they're different, but they actually are. This is more natural than this. Nature is not perfect. Nature has some variability to it. This picture shows variability, and yet it appears that it's a fractal just like the other. Here's the 8-segment Von Koch snowflake. No randomness, 5% randomness. Looks quite similar, but the edge is off. Slight difference there, a slight difference. This is more natural. Randomness makes fractals more natural. Let's look at the Sierpinski triangle. I tried this on a Sierpinski triangle. Here's the Sierpinski triangle, no randomness. Here's the Sierpinski triangle with 5% randomness. That no longer looks like a natural thing. So the conclusion I draw here is that a Sierpinski triangle is not a natural thing. You won't find Sierpinski triangles that way in nature, because nature isn't perfect, and if you don't have a perfect relationship there, you're in the fractal for a Sierpinski triangle, you get something which doesn't look very much like a Sierpinski triangle. And so I would assume that that tells me, at any rate, that you don't really have Sierpinski triangles as a natural thing. It's an artifact. It's a mathematical creation. Don't hold me to it. You know, some mathematician's going to jump up and down and scream, no, it's natural. But this is my indication, the fact that it doesn't draw very good pictures when you add randomness to it. Okay, now, the reason for today's stuff was to draw some nice pictures and show you that statistics isn't all formulas and hard things. You can get some enjoyment, some interest out of it. And next time we'll start with the real, a little more mathematical, precise stuff. Okay? See you next time.